Okay, so for this particular example problem, I highly suggest that you maybe pause the video, read it carefully, understand the scenario before you follow along with my approach. Okay, all right, so I'm just gonna go ahead and read out loud, and hopefully you can keep along here. Cars at rest at a traffic light. At the moment the light turns green, a truck rolls up the line with a constant velocity of 20 meters per second. So the truck is already moving, okay, while the car starts at rest. At the instant the truck is next to the car begins to accelerate as shown in the schematic and the velocity time graph on the right. So here's the schematic. It shows that the truck has a constant velocity of 20 meters per second, which means that it's already moving, while the car is initially at rest, waiting for the traffic light to turn green, and then it starts to accelerate away. Okay. So if you can get a visual, the truck, because it's already moving, will be ahead of the car momentarily until the car picks up speed, aka accelerate, and then a phenomenon occurs where the car will eventually pass the truck, which is shown in the velocity time graph here. Okay, so let's do it. Part A asks us to find how much time does it take for the car to catch up to the truck. Part B asks us to find the distance covered when the two catches up. And then part C asks us to find the velocity when the car catches up with the truck. And then part D asks us what time will they have the same instantaneous velocity, or aka instantaneous speed. And then E asks us how far are the two vehicles apart when they have the same speed or same velocity. And then F is how much time will it take for the two cars to eventually be 200 meters apart. All right, so let's knock out part A. Okay, part A is pretty straightforward. It says how much time does it take for the car to catch up with the truck. So in order to find time in which they meet or catch up, all you have to do is do a little setup here to help you organize your information. Here I've chosen to start with my displacement function for the car. That's because this particular function has the variable time in it. And I also know that the car is accelerating based on the wording in the problem and in the schematic and in the velocity time graph shown below. Okay. And then I'm going to go ahead and cross out, excuse me, that should have been for VI. Let me just move that real quick. Okay. All right, let's start over here. Okay. Anyways, that should have been for VI. And then, VI is crossed out because the car is initially at rest. So really, we are left with just the 1/2 AT squared term. Okay, so that's for the car, and we can use the same strategy for the truck. However, for the truck, because it is moving at a constant velocity, we can cross out the 1/2 AT squared because acceleration is 0. So it reduces it down to two pretty straightforward functions here. Now, what do you do with these two functions? Well, it says how much time does it take for the car to catch up to the truck, which implies that they have traveled the same amount of distance. In this case, the same displacement because both of the vehicles are moving to the right of the screen. So we're going to set these two functions equal because that is a true physics statement. All right, so I'm going to carry the 1/2 AT squared for the car down here. I want to carry the VIT for the truck down. So you notice here, my variable t does not have any subscripts because I know they start at the same time and they're going to catch up, aka they have the same time in this particular scenario. All right, let's go ahead and find A. I don't know what A is, but from the graph, I can find the acceleration of the car. So the velocity time graph here shows that the car is initially at rest, aka starts at the origin, and then it continues to increase at a constant rate. So it keeps getting faster and faster and faster and faster. The acceleration is not given to you, but you can find it using the information given here in the chart. Here, in the horizontal axis, the time given here is 14.3. If I just follow the given information up to the graph for the car, I go all the way to the left side where my velocity is. It says that the car has obtained a speed of 40 meters per second after a time of 14.3. So we just do slope, rise over run. Rise is 40, run is 14.3. Or you can just really just do average acceleration. It's going to be VF minus VI over change in time. My VF here from the graph is 40 meters per second. My VI is 0, and then my change in time here is 14.3 seconds from the graph for the car. Okay, so here you have two shapes. I'm looking at the car right now because I know the car is going to accelerate. So if you do your calculator work right, the acceleration of the car is going to come out to be about 2.8 meters per second squared. Well, now that we have that information, we can go back to our setup here in red. We can have 1/2 AT squared. Well, A I just found is 2.8 for the car. T is my unknown variable, and that's square. And then on the right side, my VI for the car is just 20 meters per second. So the car keeps a constant velocity. So at any point in time for this problem, the velocity of the truck it's going to be 20 meters per second. So here we notice that we have a t square on the left side, and then we have a t on the right side. So the square is going to cancel out with the t on the right. So be careful how you cancel stuff here. Don't cancel out the t. This is t squared, which implies that there are two t's, or t times t, and then we're gonna cancel one of the t's out with the one t on the right side. Okay, so make sure you do your algebra carefully there. All right. So other than that, 1/2 times 2.8 reduces down to 1.4. But then to get t by itself, I need to get rid of the 1.4, which I've decided to divide both sides by 1.4, and this is where the 1.4 comes from, and that's why it's in the denominator. So therefore t is just simply 20 divided by 1.4. So if you do that properly, you should get an answer of 14.3 seconds. Okay. All right, let's do it. Part B. Part B asks us how much distance is covered from the start line to when the car catches up to the truck. Well, here it asks for the distance traveled by the time they meet. Well, the distance is the same for both vehicles when they meet up because they left from the same starting point, aka the traffic light. So by the time they met up, they've covered the same amount of distance. So for part B, you can attack it using a couple of different approaches, either for the car or for the truck. Here I'm going to do both. You can just set up the displacement function for the car. Again, we know the initial velocity for the car is 0, so we already know the acceleration of the car. Using the previous slide, we found the slope of the velocity time graph here, which tells you your acceleration of the car, which is 2.8. So that's where the 2.8 comes from again. So if you need to rewind the video and watch the work on how to arrive at 2.8 meters per second squared. All right, and then here the time. Well, I'm using 14.3 seconds here because we just found out how much time it took for the car to catch up with the truck. So if they've traveled the same amount of distance, they met up at the same amount of time. So therefore, we're just going to use 14.3 from part A, and then we should get an answer of 286. Okay, so they've traveled 286 down the road before they meet up. Now, again, you don't have to use it, the function for the car. You can actually use the function for the truck. It'll work out both ways because they've traveled the same amount of distance. So they've covered the same amount of distance in the same amount of time. It's what it does in between that's varying, okay? AKA your velocity. All right, so for the truck, we know that VI is 20, and we know the time is 14.3. Again, the acceleration for the truck is 0, so let's go ahead and cross that piece of information out. So if you just plug and check here, VI is 20, T is 14.3, and then you should get the same answer of 286 meters, which makes sense, right? They start from the same starting point. They went to the right of the screen, a distance of 280, aka that's where they met. All right. So that's that for part B. Part C, as what is the velocity of the car? Okay, so here's the key. It says, what is the velocity of the car when it catches up to the truck? Well, we know that it caught up, to the truck after a distance of 286 meters or a time of 14.3. So to find the velocity of the car when it catches up with the truck, I'm just going to use this function VF equals AT plus VI. Why? Because I know the time already, and I know VI is 0 for the car. Okay, so part C asks the information for the car. Therefore, the acceleration for the car is 2.8 meters per second square. I know that it caught up to the truck after a time of 14.3 seconds. So therefore, I can figure that velocity out simply by using the time that I've calculated in part, A. Okay, so 2.8 times 14.3 seconds will give you a velocity of about 40 meters per second. So by the time the car catches up with the truck, it is moving at a rate of 40 meters per second. And because it asks for velocity, I just went ahead and include E's there just to be proper. Okay, let's do D and E. Part D asks you to find at what time will both vehicles have the same instantaneous velocity. Okay, so this one is pretty straightforward, not too bad. This one requires you to look at the graph here. So if I can direct your attention to the graph here, you have a diagonal, okay, aka a positive slope for the car because it's accelerating at a constant rate. And we found the rate is 2.8 meters per second squared, your acceleration. But for the truck, it is a perfect horizontal line. This indicates that the acceleration is 0 because the slope here is 0, but the truck is just moving at 20 meters per second. 20 meters per second, 20 meters per second, 20 meters per second. So the speed stays constant as indicated in the diagram as well. Okay, so at what time do they both have the same instantaneous velocity? Well, the graph tells us, okay, at this point. So when you're given two lines here, it's important to interpret the intersection point information. So this intersection point for this graph tells me that both vehicles have the same speed at this time, which is 20. Okay, so they both will have the same velocity of 20 meters per second. I just don't know what time this occurred, and that's essentially what the question is asking. At some point, as the car picks up speed, it will eventually obtain the speed of the truck. As a matter of fact, in this one, it'll keep getting faster and faster because it's accelerating. So this point here tells me that both vehicles have the same speed. I just don't know what the time is. So I know both of them have the same velocity of 20, and I'm trying to figure out what the time, like what time does this event occur. Okay, so it's not too bad. So all you have to do is set up the velocity function for the car, which is at plus vi. Again, we know the initial velocity for the car is 0, but here, well, what do you plug in for v, right? Because ultimately you're trying to find t. Well, it says at what time will they have the same instantaneous velocity. They have the same instantaneous velocity at some unknown time, but that velocity is 20 according to the graph. So for VF, I'm going to plug in 20 because they both have the same speed of 20 meters per second. Okay, I just don't know what the time is. So therefore, I can just plug in 20 for VF of the car. The acceleration is given as 2.8. We calculated. I mean, it gives to us in terms of a graph. Okay, but we found that A is 2.8. So therefore, to find t, we just have to divide both sides by 2.8. So therefore, 20 divided by 2.8 will give you a value of about 7.14 seconds. Okay, so this t in question mark in red in the graph, that answer would be 7.14 meters. 7.14 seconds. All right. Let's do part E. E asks you, how far apart are the two vehicles when they have the same velocity? Well, this one's not too bad either. Well, they have the same velocity at 7.14 seconds, which we just calculated in part D. Okay, so therefore, knowing the time, we can find the distance traveled. So I just set up my distance function here, or aka my displacement function. I know that the car is moving one way, so really my delta x will give me the magnitude, aka your distance here. Okay, so I'm just cross out vi for the car, so therefore it's just 1/2 at squared. I'm going to just plug in 1/2. A is 2.8. T here is 7.14 because that's what I calculated in part D. That's when they have the same velocity. And I'm going to square that, and if I do that on my calculator, you'll get 71.4 meters. And then I can do the same for the truck. Okay, I can do the same for the truck. Therefore, 1/2 at squared for the truck is going to disappear because the truck is moving at a constant velocity. The rate that the truck is moving at is 20 meters per second as given. The time that the time that they'll have the same velocity occurs at 7.14. Hence, the time that I've used here is 7.14 seconds. Okay, so if you punch in your calculator, you'll get 142.8 meters. Now, it asks for how far apart. So in this case, the truck has covered more distance in 7.14 seconds. That makes sense because it was already moving to begin with, while the car, it's just barely picking up speed. It's accelerating, so it's going to take a while for it to get faster and faster. So therefore, to find the answer, all we have to do is take the two distance that we just calculated. Here I have a statement. It says distance apart equals distance of the truck. Subtract it from the distance of the car. So in this case, the distance truck is 142.8, and then the distance of the car is 71.4. So how far apart are they? 71.4 meters. Okay, so that's your answer for part E. Now, graphically though, you can do this using the velocity time graph, which I would do like on an assessment on a quiz. It's way quicker as long as you know what the graph represents. Okay, so here you're given a velocity versus time graph, so therefore I know I can just find the area. The area underneath a velocity time graph is my delta x, and my delta x could equal to my distance if the object moves one way. Well, in this case it is, because both the graphs that's given is above the t-axis, which means everything is positive, aka it moves to the right and it's never turned around. So therefore, I can just be clever about this, okay? So I can just find the area of this graph for the truck. You notice here I started from the bottom and I went all the way up to the green line for the truck, which stops at 20. So this area here is my delta x for the truck. So if you do that, area is just base times height. My base here is what t was, and I found that in part D. The time here is 7.14, aka my base, and then my height is 20. So 7.14 times 20 is 142.8 meters. Now that's for the truck though. Well, I can use the same strategy and find the displacement for the car. And the displacement for the car is this right triangle. I want to start from the horizontal axis. I want to go ahead and shade it all the way up to where it touches the graph for the car. Well, this is a right triangle, so we can use the same information. The area of a right triangle is just 1/2 times base times height. Again, the base here is 7.14, the height is 20. So if you do 1/2 times 7.14 times 20 in your calculator, you'll get 71.4. Well, if you notice here, we got the same values. You know, the distance of the truck is 142.8 as indicated where my cursor is going back and forth, and we already found the same value using the displacement function, aka the distance equation if it moves one way. So all we have to do is take 142.8 minus 71.4, and of course you'll get you the same answer. Okay, so I like shading this. Why? Because it's just nice and easy. You have a rectangle and a right triangle, so it's not that hard to find the area. You just have to know what to do with the information. All right, so that's that. Part F asks us how much time will it take for the two vehicles to be 200 meters apart. Okay, well, at some point the car starts behind the truck, but it's going to eventually catch up to the truck, meet it, and then eventually it'll pass it because it keeps getting faster and faster. Okay, so therefore it will get ahead of the truck. But the question asks you, how much time will it take for the two vehicles to be 200 meters apart? So the distance between the truck and the car is 200 meters. Then that's important to understand. Okay. Therefore, I want to set up the distance function or my displacement function. But again, you notice here I'm just using delta x function, but I'm just replacing with the d because really I'm just looking at the number. I don't really care for the direction at the moment. All right, vi for the car is 0, so therefore it's just 1/2 at squared again. I want to do the same for the truck. The acceleration of the truck is 0, so I'm going to cross that out. So therefore d for the truck is just vit. D for the car is just 1/2 at squared. I know my acceleration. In the problem already, my acceleration again is 2.8. Okay, so here to find how much time it takes for them to be 200 meters apart, I would simply just take this to statement. I would take the distance of the car, subtract it from the distance of the truck, and that should equal to 200 because the question asks you how much time will it take for the two cars to be 200 meters apart. So set up the statement for the distance of the car, minus it, subtract it from the distance of the truck, and that should equal to 200. But I know that the function for the distance of the car is 1/2 at squared, which is right above here. And all I did was I carried the statement down and I substituted out a for 2.8 meters per second squared because that's what I calculated in part A, or one of the previous parts. And then the value here for D truck is just VIT, but the truck is moving at a constant rate of 20, so VI is just 20 and T is my unknown. So I left that at this. So once you get to here, hopefully your math skill is on point, that you recognize that this has a quadratic formula format. It has a T square, a T, and then some coefficient. So it's important that you practice and you recognize when quadratic is necessary. So I'm just going to reduce the statement. Okay. In order to solve this, I have to set the whole function equal to 0. To set the whole function equal to 0, I need to move this positive 200 to the left side, which turns it into negative 200. So setting the function equal to 0 allows me to use quadratic, but you have to recognize it. Anytime you have like a variable to the second power minus that variable, and then there's some coefficient involved, you can just use quadratic and just move on with your life. Okay. Here, 1/2 times 2.8 is simplified to 1.4, and then T squared is carried down. Then 20T I just carried down because that hasn't changed, and the negative 200 as well. And the whole function again is set equal to 0 because I need to use quadratic to solve for T. All right, but to solve for t, I'm just gonna go ahead and cheat here and just use a quadratic calculator. Hopefully you have this on your calculator. If not, you're gonna spend a lot of time wasting time during an assessment. So here a is negative 1.4, and then b is negative 20, and then c here is negative 200. These are my coefficients based on the function. And if I hit calculate, whoa, what happened? Oh wait, hold on. A is not negative. A is 1.4. Excuse me. So don't be whack like me. Make sure you punch in your coefficients properly. As you can see, signs matter. All right. If you do this correctly, you should get a value of 21.07-ish. Okay, so I'm just gonna say 21 because this is 0. So if you're paranoid, round it up to 21.07. I'm just gonna use 21 as my answer. Close enough for me. All right. So this is your A, B, and C. So I'm gonna go back to my answer. So again, we want to pick a variable that's, an answer that's positive because we're trying to solve for time. Time cannot be negative, so the answer that's negative 6.7 is super whack. So don't pick that answer. Time has to be positive. It's a scalar. All right. So therefore, I'm just gonna go back to this, and then I just zoom past all my work here. All right. And then if you do that again, if you understand what I did, your A is 1.4 because this coefficient here is 1.4. My B is negative 20 is because there's a negative sign in front of the 20, so that's negative 20. And my C here is negative 200. That's because, again, that's a negative 200 in the front. So make sure you look at the signs in front of the number. It matters a lot, okay? Because if you miss one negative sign or you introduce too many like I just did, you're going to get some whack answer, which might confuse you if you don't catch your mistakes, okay? Other than that, if you do quadratic carefully, like I just did with my online resource there, you should get a value of 21 seconds. All right. Other than that, that is all for this particular problem. All right. Stay nerdy. Don't be whack.